Okay, so today we're going to do a Python tutorial on exactly what I mentioned earlier, which is human activity recognition, Python, and going through an example. And just to brace yourselves, this isn't going to go into exactly details of like how everything was gotten and how to actually use it in detail. I'm going to talk about it at a little medium level. I'm going to explain all the steps, but I expect if you're interested into doing this, you should be able to look into it more about like the details of how to use it and actually the details and like what the documentation says. I'm going to give you the kind of steps or the equipment to be able to learn how to use it, not to actually be able to just copy and paste it. So table of contents, we're going to talk about what HAR is, which is also known as human activity recognition. We're going to talk to you about what the objective is and why we use it. And then we're going to go into Python, which then talks about Numpy, Panda, Scikit-Learn. And then we're going to do a quick machine learning example because I'm not sure what everyone's level is. The reason why we're using human activity recognition is because we want to make sure, like, this is a really good introduction to data science. It's relatively big data, really easy to analyze, and it's quite clean data and readily available as well. The data set that we're going to be using isn't the only data set that's available. So you'll have many, many different data sets available that you want to work on. And also, it can also stem a lot to other things as well. So human activity recognition, also known as HAR, is the use of wearable technology to monitor an individual's daily activities, such as smartphones, Fitbits, accelerometers. These things collect activity within an individual. Just imagine with an accelerometer, if you're walking, it goes up and down on the y-axis. Same thing within your cell phone. Your cell phone has an accelerometer. That's how Fitbits also determine if you're walking or sitting or standing. Why human activity recognition? It's big data. It's readily available. You probably have a bunch of data on yourself as well. And it's a lot of pre-processing, which I know you guys like, because you guys are biomedical engineers, you guys taking signal processing. These signals are beautiful to pre-process because within like activities, I think it's less than 10 hertz, but above 0.5 hertz. So you can like really be creative with this filtering technique, but we're not going to focus on that for this lesson. We focus on machine learning. There's a lot of machine learning with this. You can use a lot of deep learning methods, which I will explain. I will create an example for in the future. Typical data science project to start with. And this is like one of the examples. And human activity recognition also could be considered as passive data because it's passively collecting. You don't need to actually tell the accelerometer, hey, start collecting. And you can tell in this image right here that the individual is walking downstairs and you can see it going up and down on one of the axes because you know that the accelerometer is jumping up and down. So let's go a little bit further into passive data. Passive sensor is a device that detects and responds to some type of input from the physical environment, also known as passively collects data. Examples include GPS and accelerometer. And so I took the example of what we're going to be working on as well as just my previous work as well. This would be considered an accelerometer. Right? This would be considered the accelerometer during activities. So for example, for this one, we could tell that it's like, you know, someone's staying still. They're staying static. They're either sitting or they're either standing because there's not much movement. It's kind of staying across a very normal baseline. For this one, we can really tell that it's either walking upstairs or just walking in general because there's the periodic value of spikes going up and down for the orange and blue signal. And same thing for this signal as well. You can tell that there's a periodic spike going up and down, meaning that these would either be walking, it's a dynamic activity and it's definitely walking either upstairs or downstairs. And we can take a deeper analysis into this when you get used to the data. That's one of the things that you want to do when you go start a data science project, is that when you take a look at a certain signal like this, you could tell what type of activity it is. So within a project like this, you can do signal processing. For example, you take a look at this signal. There's so much signal processing opportunities for this. Machine learning, same thing. Deep learning, same thing. 7 common deep learning models, like Andrew mentioned earlier, or was questioning earlier, for deep learning includes the restricted Boltzmann machine, autoencoder, sparse encoding, convolutional neural networks, and recurrent neural networks. These are all really common deep learning techniques. And if you want to start deep learning, these would be the ones that I recommend. And then also HAR is a very common data to be able to collect as well. There are various different data sets available, and these are some of them right here. We're going to focus specifically on the public HAR data set, which was released really, really early. It was publicly released in 2013, but I'm pretty sure it was collected way before that. And obviously, if you want to learn more about this, self-plug, my paper is here. It's being submitted in Elsevier. It's going through revisions right now, and hopefully it'll be submitted soon. If you're interested in this, you could read my paper here. So now at a higher level, human activity recognition can be separated into input, static activities, dynamic. This is just for your understanding, by the way. It starts as an input, which is like accelerometer. It can be separated between static or dynamic. Static being sitting down, lying down, dynamic being walking upstairs, walking downstairs, and you can separate it into more. This would be kind of considered like a random forest. Am I correct? So let's keep that in mind, because that is going to be the model that we're going to be using. Now, let's continue further. I don't want to spend too much time on this presentation, but we should talk about the importance of what human activity recognition is. All right. Why are we actually using human activity recognition? You have to think about this as well. What's your goal? All right. Well, human activity recognition can monitor sports, medicine, consumer health monitoring, COVID-19, and mental health. All right. Mental health is the future, and that's what I'm working on. It can do sports because you're working on activities, you're running, it can collect that. Medicine, because if you're a patient in a long-term care, you're staying still for a very long time, it's going to monitor that. Bed sores is a common thing when you stay still for too long. So having a human activity recognition monitoring you, you can know that you should move someone just before they get cold sores or move them within an hour. Consumer health monitoring, Fitbit's phone, COVID-19, the tracing app right now. You can determine where you are versus where someone else is, and mental health, which was what I'm working on. Now, let's move on to Python. Numpy. Numpy is going to be one of your best friends. It is absolutely a beautiful, beautiful library in Python. This is what you do with all your mathematical tools and working with arrays as well. Your online documentation looks like this. In my opinion, I don't really use the official Numpy documentation. What I try to do is I just work on Stack Overflow, and I'll explain to you how I find my functions later. All right. So some applications of Numpy include quantum computing, statistical computing, signal processing, image processing. So whatever you think you could do in MATLAB, whatever you want to do in MATLAB, you have to import Numpy, and then you'll be able to do the same thing. Right? So for example, earlier, what Martin said was the sum function. Sum function would be used in NumPy. Python doesn't natively have a sum function, I don't think. So you'd be able to call in NumPy, and you'd be able to call all these different functions such as sum, variance, standard deviation, etc. So an example in NumPy is you import NumPy as NP. So the first two would be represented as import NumPy, so you're importing NumPy. But every time you call NumPy, you don't have to just say the whole name. It's a lot longer. And in typical data science and coding, you do it as NP, so that when you do it, it would be np.sum. This is supposed to be lowercase, by the way. They uppercased it when I was writing it into PowerPoint. So it'd be like np.sum of your array, np.mean of your array. You could technically just do import NumPy, and then it'll be numpy.sum or numpy.mean. NumPy is also very, very good with arrays as well. Within the NumPy is known for arrays actually. So commonly in Python and natively, you work with a list, which is very similar to arrays, but arrays is just a more efficient method. And defining array, an array is a container object that holds a fixed number of values of a single type. The length of an array is established by the array is created, and after creation, its length is fixed. So an example of an array in MATLAB would be just any signal, but just fixed. For example, if you have a sinusoid, it's a 1/66, right? That would be considered an array. And to be able to create like any, like from a list or from anything else into array, you do np.array of those values, or you create it like this, where it's just square brackets. So the round brackets represent whatever you want in your function, but the square brackets represent the numbers or your go-to array in the future. And this is what one looks like. And sorry, just a quick tip. If you guys have any questions, please write them down, and then we can go over them after I finish these slides. So Panda, which is absolutely another beautiful library in Python. Panda is the main go-to library for me to be able to import any like data into it. For example, if I wanted to import a CSV file or a text file, Pandas is the go-to. The native Python is also available too. I don't like that. I think actually you guys worked with that. Yeah. You guys did work with that. I think it was like for file in or something, and then you read line by line by line. That was one of the methods. Pandas is a lot more efficient. Panda creates a data frame. And a data frame simply represents a table of data with rows and columns, the list of columns and types of those columns in the schema. A simple analogy would be a spreadsheet with named columns. Or what I like to say is data frames could also be represented as either a matrix or a table. And the difference between a matrix, sorry, I wouldn't call it a matrix actually, I take that back. The difference between a data frame and a matrix is that data frames have header files. So for example, usually in a CSV file, you have a heading file. So for example, let's say we're collecting data right now with ECG. You would have, for example, the voltage up top, and then you have the values going across. That would be your heading file, your voltage, right? Also known as, I guess, quote unquote, your y-axis. But the thing is, within the table, you could have multiple different signals. And with Panda documentation, again, I don't use it too much. I prefer just to go into Stack Overflow and then just use something on that. This is what it looks like though. And I'll show you guys exactly what I mean, like how to actually use it later. But I forgot to include the import part, but it's import Panda as PD, same thing as import NumPy as NP. PD is the short form of it. So it'd be like pd.csv read and whatever value inside. And CSV read is just a function available in Panda as well. And this is like pretty interesting because like I found out last night when I was working on it was that you could read almost any file with CSV_read, even if it's a text file. I think that should be fine, but that's what I found last night. Okay, so Scikit-Learn. This is the things you're probably like looking forward to learning. Scikit-Learn is your best friend for machine learning, especially when you're starting off. There's other stuff like TensorFlow and what was the other one? There's TensorFlow and something else. But anyways, Scikit-Learn is your go-to, and it's a really nice one. Go to machine learning library. What did I mean by that?
I think you probably meant like the library that you go to when you want to do any machine learning.
Yeah, but oh, Paul, yes. Yeah. No, you guys are right. You guys are how did you guys know more about my slides? You're right. It's the go-to machine learning library. You guys are correct. Thank you guys for that. It's your go-to machine learning library because it's so useful. It's so good. It's so simple too. It's so ready to understand. Thank you guys for that. Thank you for understanding my slides. The documentation.
Don't worry.
The documentation I highly recommend to use. Scikit-Learn has the best documentation in my opinion. It makes it so easy to understand and to be able to kind of, they give you an example as well to copy and paste and then work off of that. I find that Scikit-Learn is actually, the documentation is very similar to the MATLAB documentation. And I find MATLAB documentation to be stunning. All right, so this is what it looks like, but this is like just the home page. If you want to go in a specific example, obviously you go into whatever. All right, so let's do a summary. I'm going to question you guys now. What is the main purpose of NumPy and when would you use it?
It's used for arrays and math functions.
Correct. Statistical analysis, mathematical operations, and arrays. Okay, Panda. Someone answer besides Paul.
to use for like data frames and reading CSV files and having your data coming in with like headers.
Correct. Scikit-Learn.
Machine learning.
Yep. Beautiful. All right. So now you understand the basics. These are your go-to three libraries. I also forgot to include, there's also Matplotlib as well. But the thing is, I don't think I need to explain that one because it's literally plotting. I don't think there's much else to say. The documentation's a little strange for that one. I have a hard time. I used to have a hard time with that one. It's not like if you go from MATLAB to Python with plotting, MATLAB is so much easier and so much better. But obviously we have to plot in Python as well because you always have to visualize. But now, machine learning. Let's go over a little bit of machine learning. Actually, before we go that, does anyone have any questions regarding what human activity recognition or anything in Python?
No,
No questions? No one?
I'm good.
Okay, fantastic. Let's move on to a machine learning example. Let's talk a little bit about machine learning. Right. The goal is to use features to be able to create a model and predict other data and give an accuracy based on the test label. This is probably a run-on sentence, but I wanted to put everything that you had to do into one sentence. And the steps include creating a feature set from your input. You want to train your model, create your model, and then you want to test your model, predict other data. And then finally, you get your accuracy by testing your label. Right? So just imagine if you have a data set, you want to be able to extract features from it, you want to train a model with this, and then you want to test your model and you get an accuracy. Right? These are the steps that you want to do into machine learning at a very high level. We're going to focus specifically on creating a feature set because I think this is probably the most important part. And then later on in future lessons, if I get good feedback from this, is that I'll be able to also teach you guys how to train a model, test a model, and get accuracy. With more complex stuff, like actually know how to, work with the hyperparameters and such. Within today's example, we're going to do something very simple, such as random forest. There's not many very parameters. It's just mainly copy and pasting from online. You just have to know which ones to copy and paste. But we're going to focus specifically on the feature set. So the feature set, the goal is basically to extract features from your data. So you guys took 772, I'm assuming. Why don't you guys shout out some features that you guys extracted from your project or features that you would want to extract from just a general data set?
Mean, variance, other ones, I guess.
Zero crossing, RMS.
Form of frequency, yeah, that's good. Anything else? How about like kurtosis? How about like skewness? How about like the really random ones? What happens if you go into the frequency domain? What happens if you go to another domain as well, right? Their features are endless. That's my whole point of this.
Okay.
Now we go further into the feature set. Once you extract those features, what do you do with them? You have to create a matrix of that. And some of you guys I think helped with this 772 project, and I hope I explained this correctly, but I think this is a better explanation, is that you want a feature table, or a feature matrix, which is basically your features is down one column and your samples are going across the rows. So for example, if you have, like you guys said, the mean, the variance, the zero crossing, you would have one value of the mean, one value of the zero crossing, one value of the variance per sample going across the row. I have an example in the next one, which is like this. All right. We have one sample right here. Sorry, one sample right there. Another sample here, 3, 4. So we have a sample going across the rows. And then as well, we have feature 1 and feature 2 going across as well. All right. Does that make sense to you guys?
Yeah.
Perfect. And then also in typical machine learning as well, in a typical like machine learning fashion, you also have your labels on the last axis. You could do this or you can keep it separate. It doesn't really matter, but you have your classification label at the end. And this is just a quick machine learning example. I'm not sure if I went through this with you guys yet, but with machine learning, basically, you have, for example, if you want to classify oranges and apples, you would have your features such as weight and texture. Right? These are features of these fruits. The weight would be one value going across. The weight of this sample one would be 155. And we still know another feature being texture, it's rough, right? And it's labeled as orange. So if we plot this on a 2D plot, we get rough, smooth, and the weights on the sides. And your goal is basically to train a model so that it can create a linear separation between these two fruits. This separation could be linear, nonlinear, or even unseeable in a higher dimension. Right? But the simplest one is linear. But also your model can also separate it in different ways as well, such as this or that. Right? It could create a separation. It could create a separation between oranges and apples in a way that it could be overfitting it or underfitting it. Right? So you have to be careful about that. And this is where it comes to actually understanding what your machine learning model does. Now, let us go through Python. Actually, before we do that, does anyone have any questions with machine learning?
Well, just one thing about that example.
Mm-hmm.
The weight is kind of irrelevant.
The weight is
Right.
kind of irrelevant?
Yeah, because you could have like a really small orange and it would still be an orange because of the roughness, right?
Yes.
I mean, I'm just nitpicking the example, but
yeah, this is just an example, and it's just
Okay.
to kind of make it very like understandable and relatable to everybody, because everybody knows, the weight, what a weight is and what a texture is. So,
Oh, okay.
Yeah.
Thank you.
Any other questions or comments? Okay, let's go into Python. So what we're going to work on is we're going to work on a HAR data set, and I'm going to go through the data set with you. So I'm going to send you all the information, and then you can try this on yourself as well. I'll send you the publicly available data set, zip file, and everything. You guys will have everything. All right. So we're going to open the folder, and I'm going to explain the data set a little bit. Okay. So within the data set, it's human activity recognition, which I mentioned using accelerometer to determine activity. We have 30 subjects. The activities, also known as the classification labels, because this is what we're trying to classify, includes stationary. Stationary. Includes stationary walking. Okay, stationary is not part of it, sorry. It includes walking upstairs, walking downstairs, sitting, and lying down. And stationary. What is stationary?
Not moving.
Standing.
As a baseline.
Standing, that's what it was. Standing,
Oh.
thank you. Because they're sitting, lying down, and standing are the three static ones, and walking upstairs and walking downstairs are the dynamic ones. Sorry, thank you. I think I either spelled that wrong or it said stationary, standing. But yeah, stationary is just standing. So those are the 6 labels that you want to be able to classify. In your head, think about this as a data scientist. Think about this as an engineer. What would be like, would you be able to actually differentiate those? Would you be able to actually see an accelerometer signal and say, these would be like kind of like the small, minute details that make it different from different labels? Just think about this. This is a rhetorical question. And the data is being collected through an accelerometer, gyroscope, and magnometer. It uses a window which has 128 samples, which represents 2.56 seconds. So every window that you have will be 2.56 seconds. But since we're doing it in coding or in a digital manner, it's 128 samples. Your data set is 7,352 by 128. Right? And this is just for one of the signals as well. So this would just be for example, the x-axis of the accelerometer. So you could see how this is big data, because you have accelerometer, gyroscope, and magnometer. You have the XYZ of all 3 signals, so that results into 9 signals. And you also have 7,352 by 128 for each one of these signals. So it's whatever that value is times 9. So I think that's like, to start off, this is like a really like medium to large data set. Right? You have 7,352 samples going across. And in each sample, the reason why it's 7,352 is because that within each activity, I found that they spent around a minute to a minute and a half, which resulted in 40 seconds. Sorry, 40 seconds times. What am I saying? Yes. Sorry. My bad. So the time spent per each activity is around 1 to 1.5 minutes, which you could also break down to 40 windows because it's 40 times 2.56. So it's around there. Right? That makes sense so far, right? This gets a little bit convoluted because I didn't do the proper math. I didn't show the results. But basically, you spend about 40 window samples in the whole entire as one subject, right? So you have 30 subjects, you multiply it by 6 because there's 6 activities, and you multiply it by 40 window samples, you get approximately 7,352. That's how you get the number of samples by windows. And remember that it's samples and then windows. The 128 is just one window that you need to focus on, but you want to focus on specifically each sample going across. The number of row depends on the subjects and length of each experiment. If you don't want to kind of understand this part, which is kind of confusing in my honest opinion, you could just say that number of rows, it depends on the subject's length of each experiment. Does anyone have any questions in regards to this? Like just this whole one slide? Does it make sense to you? That's the real question. Are you guys confused?
I think it makes sense.
Okay, who said that? Who said that?
Where did the 6 come from?
The 6 is the 6 classification labels. So yeah. Because if this makes sense to you, then you're lying. I'm just kidding. But you kind of are lying because this is kind of, no, you're not lying. But this is like one of the, I'll show you more in detail so that you guys can really understand it. But this is one of the signals I showed you guys earlier of there's actually a video online that you can watch. I'm not going to watch it today, of like someone doing activities and then collecting it on accelerometer. Okay, let's go through the folder. So this is what the folder is. When you download it, you have these 3. Right? Oh, sorry. These 2. And you go to UC HAR dataset, you have all this information. You have the activity labels, which includes 1, 2, 3, 4, 5, 6, walking upstairs, sitting, standing, and laying down. You have the feature info of what they extracted for their works, right? Including, for example, the mean, standard deviation, the median, etc. They give you some information about that. They actually give you a whole feature list. These are all the features that they extracted, which is a lot, right?
Yeah.
And then they have a README. And I think from the README, I think the main things that you guys really want to kind of know is that basically you have 2.56 seconds of each window. It's a sliding method. So 128 readings per window, which is what I mentioned. They already did the filtering before, so you don't need to work on the filtering for this project, and that's why I chose it. Right. They talk to you about like what pre-processing techniques they use, but our main focus is mainly to go through an example like this. Right? So for each record, it provided a triaxial, basically X, Y, Z, acceleration, angular velocity, gyroscope, and they have a feature vector as well with 561. So you could technically just apply machine learning if you really want to, because they already have this data set. Like they already have all the features ready. They have all this information ready so that you could just toss in a model. But we're going to start from a little bit behind there, and we're going to extract our own features as well. It's not going to do the best, but this is more of a learning process. Right. There's all this information that you can read about. It helps a lot because it helps you understand what the data set talks about. Let's see. Yeah, that's about it. And then now we go into the test and train. So within this x_train, this is a text file. This is the 561. And if my computer was long enough, it would go 561 values across, like going across this way. And then it would just be all the samples going that way because these are 561 features per sample. Right? But we're not going to work with that. And then also the subject train as well. So for example, each row would be represented as subject one, subject one, subject one, subject one, subject one, going down to subject three, subject three, subject three, subject three, right? So each row would be represented as another subject. Same thing with the Y value as well. The Y value would be represented as 5, 5, 5, 5. So like this, the row 1 would be activity 5, row 2, row 3, row 4, row 5. These would all be activity 5. Activity 5, I think, was one of the static activities. I can't remember exactly what it was, but we had it a second ago. And then we could use xtrain, but instead of using xtrain, we go into the inertial signals and we could use one of these. All right. One of these, I think my computer is long enough to be able to separate. No, it's not. Okay. Anyways, it's not long enough to be able to show you all 128. But each row, this would be considered one row right here. From here to here is one. Let me open it actually. Sorry. Uh-oh. Yeah. So this would be considered one row right here. It just happens to be that my computer is not long enough to be able to do it. But that's one row, which has 128 samples for the window, and that would be considered one sample of 2.56 seconds, right? And you would have, how much was it? 7,352 rows going down, making a 7,352 by 128, which I mentioned earlier. Right. And we're going to be working with specifically just this one signal. And then we're going to replace that signal with x_train. So we'll still use subject_train because we need to know the subjects. We also need to have the labels, which is y_train. Right? So we'll be able to use this and we'll just replace the x_train. And it'll make more sense once we actually get to the Python example. Okay, so let's take a quick 5-minute break. Does anyone have any questions? Okay, so how's everyone feeling? Is everyone ready to continue in the next part?
Yep.
Yep.
Martin, you there?
Yes, sir.
Okay, cool. Everyone's good? Hey, Russell's here. All right, let us begin in the next part. So now we understand how kind of the data set is kind of laid out. Every data set is laid out differently too, so please remember that. But yeah, let's open Jupyter Lab. I opened Jupyter Lab through terminal. And uno momento. While it opens, you could also do whatever coding you want to do via other method as well, such as Python or Spider, PyCharm, etc. As long as you have the libraries. Sorry. Okay. Cool. So this is what I'm using Jupyter Notebook because it makes it simple. I can write notes on the side rather than having comments. I just replace these with markdowns. And if you have used Jupyter Notebook or Jupyter Lab, you know that it's just literally a notebook. You can print it out afterwards. It's really easy for documentation. I'll put this onto my GitHub as well so that you guys can download, as well as I'll share this video as well as PowerPoint so that everybody can be on the same page. All right. So today will be the Python tutorial for you guys, which is February 8th. The goal is to teach you the fundamental topics of Python, and we go through specifically this example. I make modifications of this LSTM for human activity recognition time series classification. It kind of goes through this, not really, but the overall goal in the future is to be able to actually go through this example right here, because this example is really good. I find really good for starting with data science. Okay, so important libraries. Where are the important libraries? Okay. Methods. We're going to use Panda and matplotlib to save the data into tables and plots respectively. Panda, as mentioned before, that's how you import data into data frames. And then the matplotlib, which is literally matplot library, is to be able to plot the data so that we can see and visualize it a little bit. And like I said, it's not the best. I don't like it compared to MATLAB itself, but it's one of the plotting libraries that's quite simple in Python. So data frame, I'm just copying what I wrote from the slides. It's a data frame. A simple analogy is that it's a spreadsheet. So as mentioned before, import panda as PD. This is just a common way to do it. Import matplotlib as matplotlib.pyplot as PLT. So whenever you want to plot something, it'll be plot like that. How do I know this? You kind of have to look at the documentation to be able to understand this. And with matplotlib, I feel like I can't really explain it to you. Like you literally just have to copy and paste an example, and you'll have an example in this, and it'll make sense automatically if you understand Python and then go into if you understand MATLAB and you go to Python, it'll make sense automatically once you understand like, oh, this is like the syntax. Everything will be the same. But yeah, so I restarted this kernel so that there's nothing readily available. But I had to run that area right there. And these are just quick shortcuts that you're probably gonna see off screen of me just pressing stuff. And just to be able to kind of understand like where my data is, because within when you're working with code, I'm sure that everybody has dealt with this, is that you don't keep everything into one file in one folder, sorry. You kind of separate the folders, right? So I'm just gonna print out where my current directory is. Import OS, which stands for operating system. This code right here, these 3 lines, can basically get you what your current directory is, which is in my case this. How did I find this? And do I know this myself? No. What I went online was Python find current directory. Go to Stack Overflow, see an example, copy and paste. Well, obviously read the description first. Don't just randomly copy and paste, but that's what I usually do if I need to find something specific. Right? So my current directory is user/bin/desktop/python tutorial. So as mentioned earlier, we know that the Python, like the folder that we're working with is going to be in body acceleration X train, right? Let's go back to the folder again. All right, so we start off with this output data. So we have our Python in here. We go into the folder, we go into train, and we go into inertial signals. Right. So the steps to go into that is basically, and this is important because like you're going to be working with different directories, is UCI HAR dataset, train, inertial signals, and then your actual signal. So in this case, it would be UCI HAR dataset, train, inertial signals, and then the file name. I separate into path as well as file name. And then I combined all 3 strings together of CWD, which is current directory, path, and file name. And it'll get me something like this. Now we go into actually extracting the data. Remember when we talked about panda, pd.read_csv? Well, how do I know like this is like the function, right? Panda read text file. I already had it. All right. So again, my beautiful, like there's also the panda documentation, which I don't exactly like. I'll open it and show you guys. This is what it looks like. All right. Going through it, it's not bad, just don't prefer it. But Stack Overflow, beautiful. They have an example. I read through what the question was, and okay, this one works. There's also this one, there's also this one. Basically, you find an example that works with you, you test it out and see which one works and which one you like. I found that this one works really well with me. pd.read_csv, you put in your file name, you separate it with space, and a header is none. I tried it, this part messed up my data a little bit, so I just kept it as header equals none. And then if you want to learn more about it, you go into the actual documentation, search up what header means. Oh, header means that does it have actually a header file up top or it doesn't, right? So my tip to you guys is find an actual example on Stack Overflow, try it out, see if it works with your data. And then afterwards, go to the official documentation, which is like Panda, and then figure out what you like and what you don't like, customize it accordingly. Does that make sense to you guys? Thumbs up? All right, great. So yeah, so now we know that df pd.read_csv, and then f header equals none, delim white space, delimitate the white space equals true. Right? These are some customizations I found, and I think I just found an example online and I just copied and pasted it. Now this part right here, print, this is the first 5 windows. So df will now save our values, our specifically the body acceleration x train, into df as a variable. In Panda specifically, remember that if you have a data frame, df from Panda, they have this function called head. Right? Head is basically something that shows the first 5 samples of your data frame. There's also tail as well. So you can do df.head or df.tail, and it'll be the first 5 or the last tail. Makes sense, right? Head being top, tail being the bottom. These are just functions that you'll understand over time. And these are also steps to be able to kind of visualize what you're actually taking a look at as well. So in this sense, what happens is df is saved and I print the first 5 samples of the whole entire data set. All right. So it'll be 0, 1, 2, 3, 4, indexing on 0. And then there's going to be all the columns going across, which is 128, because remember, it's 128 going across, 7,000 something going down. That makes sense, right? And for those that are skeptical about, oh, how do you know it's actually doing it? Let's print out the first five samples. So within data frame, you have df of 0 because it's the first array, which is going to be this one right here, going the row across. And then you're going to only print out the first 5. So we should expect this one, this one, this one, this one, and this one. Which is not what we get. What do we get instead? 0, 5. Oh, sorry, I missed this one. Yeah, so we got 0.00181, correct? 0.0194. Sorry, okay, so it's going column-wise, not row-wise. That's going column-wise. So you got 0.001094, correct? 3531, correct, etc. This is just to confirm that this is your heading file, which is the first 5 values. And now we have this guy, right? Oh no, yeah, this guy. So within data frames too, when you have something as a Python Panda, you're gonna have to use ilock to be able to get the specific row. So I find that with this, I still have a hard time sometimes. I get confused. Oh, should I use ilock? Should I not use ilock? Arrays don't use ilock. So for example, if df was an array, you would just do df of 0. But just to show you that it doesn't work. Oh, it doesn't work. Sorry. Okay, that doesn't call that. But in typical practice, what you want to do is ilock with data frames, which gets you the row across. All right. So you basically get from 0 to 128. Without ilock, I'm assuming it gets you the column, but the thing is, remember that our samples are going across the x-axis, not the y-axis. So that's why we do df.ilock 0, which is the first one going across the x-axis, across the horizontal, getting you that entire one sample of 128 samples, 128, which is the window. And this is one of the signals. So I know that this is one of the activity signals. I know that this is specifically, I think, number 5, which is, I don't remember what number 5 is, but whatever that activity label is, number 5, because I've worked with this data set before. To you guys, it just might be a random signal, like, what is this? Right? What is this? The thing is, okay, so we know that. So let's get a little bit more comfortable into what we're actually working with. But before I continue that, does anyone have any questions regarding any of this up here? Up to plot. No?
Good.
Good. Okay. I think the other thing I didn't really mention is that plot. Just imagine this, and if you're doing it in Python, just imagine it like this. Right? Just imagine that as this. It's just that you have to call the library in advance, that's why. Okay, now let's get a little bit more comfortable. Now, let's load the subject number and the data label so we know what exactly we're working with. All right, so we do exactly the same thing. We have the path, we have the file name. The path is different because it goes to UCI -lane. It doesn't go into that extra folder. Do the exact same thing, pd.read head. All right. Oh, so we know the first 5 samples are 1, 1, 1, 1, 1, which are subject 1. Right? So these first 5 samples are 100% subject 1. And yeah, now we do the exact same thing for label. So we know that it's still in the train folder. It's y_train.txt. That is that's the new file that we want to work with. We open it. I don't do head this time. And the reason why I didn't do head is because I wanted to take a look at the bottom as well. So we know that the first signal that we looked at, which is signal 0, is subject 1, as well as we know it's activity 5, okay? Which in this case is standing. So when we take a look at the signal, this represents standing of subject 1. So the reason why I wanted to print out the bottom 5 as well is because it's number 2. So let's go back to here. Let's print out the bottom 5 as well. So we know that subject 30 would be sample or row sample 7351. We know that in row sample 351, it's subject 30 doing class activity 2, which is walking upstairs. Right? And I think I showed you in the PowerPoint that walking upstairs is a little bit easier to kind of see. So I print out some information. Label is 2. The subject is 30. Right? Everyone good so far? Good so far?
Yeah.
Okay. Now what we want to do is we're taking sample 7351, right? 7351, very last one. So we want to plot that one. Exactly the same thing as MATLAB, just have the PLT in front of whatever you want to do. Plot df.iloc 7351. And then title, obviously, X label and Y label. I'll explain those after, but I really want to focus you guys on specifically this one. Right. We're plotting this one specifically. So we know that we're plotting specifically label 2 of subject 30. What do you think it's going to look like? Do you think it's going to be recognizable? Something like you've seen before in one of the examples I showed you guys? What do you think walking upstairs will look like? So we're working with specifically, where is it? Body acceleration X. So that means acceleration for the X axis. Right? Do you think you'll be able to recognize someone walking upstairs with the signal? Okay, how about this? Let me rephrase this. If you have an accelerometer of the x-axis specifically, and you record yourself walking upstairs, what do you think that's going to look like?
Which way is the x-axis?
The x-axis is going across this way, like horizontal to you.
I don't really know how to describe it, but you think maybe a little bit. It might be like up and down.
Yes, perfect. So these are the type of questions you want to ask yourself when you're working on a project. Does this make sense? Does this make sense that this is the x-axis acceleration of someone walking upstairs? Does this relate to what you're actually doing? Don't just think that it's another random signal. Make that connection. Just like when you're working out, you want to make that mind and body connection. Same thing with coding. It's that mind and coding connection. You have to understand this makes sense because the accelerometer, if you think about it, you literally walking up and down, upstairs. You have that jolt, which affects the y-axis, the x-axis, and the z-axis. Right? So you can easily tell that this is a walking method. You don't know if it's upstairs, downstairs, or straight, but you know it's a walking direction. Right? This makes sense. Now, obviously, with title, X label, Y label, it's the same thing as MATLAB. X label, sample, Y label, amplitude.
Yeah.
And do you guys know these, by the way, like the percentage D to be able to put that value in? Anyone?
Yeah, use them for MATLAB.
Okay, perfect. I'm not sure if this was applicable, but fantastic. Okay, does anyone have any questions so far? Nope. Okay. So let's go into feature extraction. Now we're going to try to get the features. We're going to focus specifically on average, variance, max, and min. Recall our feature table from the orange and apple example. So what is going to be our vector sample size for this specific example? And I give you a hint that we have 7,352 samples and a window size of 128. What will be our final vector size of all these features?
of just the four, like the average, variability, max, and min,
Yeah.
it would just be 7,352 by 4.
Good. Good. I'm actually really happy that you got that. I'm really happy that you got that. That means that like you guys are absorbing something I'm saying, which which is good. Thank you, Andrew. That is exactly it. I was hoping that this 128 would throw someone off, but I'm happy that you guys got that. Okay, perfect. Now, okay, that is exactly what our goal is. That is what we want to be able to achieve, because we only want 4 features, right? We only want 4 features, and we're going to have 7352 samples. So now our method that we're going to do is we're going to use NumPy. We've used Panda. We've used Matplotlib. We've done that. We've introduced the data set. Now we're actually going to get to that nitty gritty, that beauty, the fun part, in my opinion, is the NumPy. NumPy is a mathematical tool. If you want to learn more, W3 has a really good source of like where to learn this type of stuff. And when you want to find something, just Google literally NumPy find mean. Remember when I showed you about Panda find CSV or import text file? Literally the exact same thing. Do exactly what I mentioned. Just find something on Stack Overflow and then go into documentations afterwards to customize it. Right. So first things first, import NumPy as NP. So with the df_average is a new variable that we want to say. We want to do np.mean of the very first row. Remember, iloc represents the row, which is 0. Right. We get this value. Okay. So let's take a step back. How do we find the mean? Find mean Python. There's a bunch of different ways. There's a native way, but NumPy is just the most efficient. So you also have to include that. NumPy.mean. You find this. Okay, documentation. In this case, documentation does work. All right, you do NumPy of mean of your array inside, and that's it. It's actually, I think, almost identical to MATLAB, except it just has NP in front. I think Python is very similar to MATLAB in general. It just has these external libraries that you just have to call in advance, and that's about it. But yeah, so we found the first row average to be 0.0022. Right? Taking a look more into the mean and NumPy mean documentation, if you want to take the mean of the entire table, rather than going row by row by row by row and then meaning it, something like very tedious, you could literally just do the entire matrix and find the mean across. Similar to MATLAB, similar to Python, you work in matrices in Python and MATLAB. You don't go line by line by line by line or something tedious like that. Right. So you do np.mean of the entire df, but you do axis equals 1. Okay. So let me tell you why you do axis equals to 1. Remember how df.iloc is the row across? Axis.1 does the mean across each axis. So in this case, rather than summing them columnly, which gives you what? It gives you 1 by 128 because it would sum column wise, right? And this one, it'll be 1 by 7,352. And sorry. And obviously I plot the head, right? And just to confirm that I'm doing this correctly, I compare the first df average, which is just the one across, with the very first one of df average here. Right? And just to show you guys, if you do np.mean of df, this is going to give you 0 to 128, right? So it does column-wise averaging, so column-wise averaging. But what you want to do is horizontal-wise averaging, because you want to keep all the samples. Right? Obviously, there's a bunch of different methods to be able to do this. For example, if you don't want to do the axis, if you want to take a longer route, you could do np.transpose, which is another method of NumPy. All right, I'll give you the exact same example, same response. There's a lot of different ways, but you're gonna have to practice and train around, get tips from other people to see what is the most efficient way. And the most efficient way is this one. Honestly, I didn't even know that, I didn't know about this one. It's not until I did this that I realized, oh no, I don't want it to be column wise. And what I did was I just searched up NumPy mean row wise. And then I found calculating mean across dimensions in 2D. Stack Overflow again comes amazingly clutch in this. And then you read some of it and you check in the documentation, you confirm, etc. So continuing forward, now we continue extracting our features. We have df underscore var for the variance, np.var variance, and then we do the exact same thing. We do it row wise, which is axis equal to 1, max, min. All right, so now we have our 4 feature vectors. Does that make sense? Does anyone have any questions regarding to this? Okay, great. If nobody had any questions, now what we're going to do is we're going to stack them together. We're going to put them all together because right now we have a 1 by 7,352, 1 by 7,352, blah, blah, right? We have 4 of these, but we want to put them together. Right? You may think, oh, let's just put them like this. Something like that, right? You want to put them across each other. That might work. You can try it. Right, it doesn't work. No, that's not the right way of doing it. What this does is basically it creates one array, literally just one array, and then beside it makes another array. Right? They're not concatenated together. So one thing you want to do is continue using NumPy, and they have this thing called stack. All right. So let's take a look at np stack. All right, this is the documentation. Joins a sequence of arrays along a new axis. Fantastic, isn't it? All right. Same thing, axis equal to 0 or axis equal to 1. Okay. So now that we have that, what we want to do is NumPy of square bracket of all of these guys, concatenating them together for one column, one column, one column, one column on axis 1, right? Because we want them column wise. And in this sense, when we print this out, it'll be exactly what Andrew said. It'll be 7,352 across 4. So we could also print, what is it? The shape? Sorry, I'm getting confused with MATLAB and Python, like working between the two. We get exactly what Andrew said, 7,352 by 4. You could tell is 7,000. I'm just going to say 7,000 rather than all the numbers. 7,000 across the rows, each sample, and then 4 features. So this would be represented as our beautiful feature vector. So with NP stack, let's go back to this one really quickly. We have the 4 features across in axis 1. The reason why I know like axis 1, all that type of stuff is because I did trial and error before. I didn't get this on the first shot. What I did first was NP stack. Of this. All right. This is what I wanted to do first. Didn't work. I'm like, okay, let's do square brackets because the square brackets because that's what something is common. And sorry, what I did was double brackets, double round brackets. Oh, you know, that works, but that's not the right way. That gives me 4 by 7,352. That's what I want. I want it the other way. So what I did was, okay, let's take a look at the documentation, and I found that axis 1 would give me the right one, where it would be 4 by 7,000. Yeah, 4 by 7, or sorry, 7,000 by 4, because it would stack them across column wise. And that's kind of like my process of thinking. It's like starting off with the most basic and then getting it to exactly where you want it to go. And now we have our feature vector, right, which goes across like this. We're going to make sure that it actually works as well. So we want to print out df underscore average 0 to 3. So it would be the first 3. We're expecting that this first column, this first print will be these 3 first values, var, these 3 first values, etc., etc. Right? Which it does. Because you could take a look at this. Obviously, the notation of e to the -3 or the precision is a little bit different, but they are the same value. Right. This one is rounded to 0.00009, or this one is 8.6. All right. Now we have our feature vector or matrix, or it's sample by features, where samples is the row and features is the column. Now let's go into machine learning. But before we do that, does anyone have any questions?
I have a question about the feature vector. You see the first line, how it has 2 square brackets?
Yeah.
Is there any, is that how it's always going to be? Because I think I was running into a little problem with that the other day.
Mm-hmm.
Like it just seemed like I had to do like a couple more things in order to extract like I had to find the maximum of it was just a 3x1 vector. I had to find the maximum and then the location of it, but then it had like double brackets, and that gave me a little bit of trouble. And I was just like, why can I not just take away the double brackets?
Right. To be honest, I don't even know why you need to do the double brackets. I 100% agree. It's just something to do with the documentation and the notation of like how you're actually doing it. Right?
Okay, yeah.
So like with NP stack, I always find that it's always double brackets, and yeah.
Because if you just were to create an array that's like, if you manually were to put in all the numbers, just like np.array and then manually put in, would it have the double brackets?
You still have the double brackets. So if you only
still...
wanted one, for example, like np.stack, you would always still have to have the, like this, like you would still have to have the double bracket.
I think the reason you need the double brackets is to specify what you're actually stacking. Otherwise, if you're just putting input arguments, it doesn't know what you're stacking and what's actually like a property of the stack.
Yes, that's definitely correct, and that's why the documentation helps a lot, because that explains it.
But like also like in the output there's the double brackets.
Oh, yeah.
Because I think that's what was giving me the issue, because I was trying to find like, but then yeah, I just had to, when I would put it, I'd do like whatever, let's just say it was the feature vector, it was like feature vector bracket 0 bracket, and it'd be like the max of that. That's what I had to, I don't know.
I'll have to double check that, but let's talk after, or I'll be able to help you after on that one, because I'm not understanding the full context of that.
Yeah.
Yeah. Also, sorry, before I move on to the next part, and NumPy also has, rather than doing axis 1, if you guys really want, there's also another method called hstack or np.vstack. Can you guys guess what H and V stand for?
Horizontal
and vertical, correct. All right, so these are also other libraries, but other functions, but you could use also just a stack in general and just do axis equal to 1. Yeah. Does anyone else have any questions?
I have an unrelated question for tutorial 2. Is the deadline next weekend?
Sorry, say that again.
When's the deadline for tutorial 2?
For tutorial 2? This Friday, or the Saturday.
So it was extended, right?
Yeah.
It was because of the mistake? He just added another week to it?
No, it's because of the professor wasn't able to teach you guys a proper material, I think.
Oh, okay.
Yeah. No other questions? Okay, let's go into the last part, which is our beautiful machine learning. So remember that block diagram I showed you guys earlier? Well, it's similar to a random forest tree, right? So what we're gonna do is we're gonna actually create a random forest. And the documentations are here for these, and I highly recommend using them because they're so nice. Just like, this is like so beautifully written. It's literally just Scikit-Learn, random forest, gives you all the documentations about the parameters, and gives you an example at the end. Oops. Right here. Oh, yeah, right here. It gives you an example at the end, and the more you read it, the more it makes sense. So let's go into train split and test split. So we're gonna represent our data as just like a complete data set. We're not gonna split it. We're not gonna use the other files that they gave for this specific example. We're just gonna split them because I want to introduce to you guys splitting. So Scikit-Learn, which is Scikit-Learn, you have to import a bunch of different libraries, and honestly, I don't know exactly which ones to import. Sometimes I just kind of copy and paste which specific examples I have, and the common ones I know, which include random forest classifier, train test split, and accuracy score. How do I know the dot ensemble, dot model selection, dot metrics? No idea. So I know these are the libraries I need. Now we have to split the data that we have, right? Because we have the feature vector. Now we just have to split it between the training and the testing. So we set feature vector as X, and we set our labels, which is from what we took way back in the day, way back in the lesson, as Y. Right. And the notation of uppercase X and lowercase y is I took it from this, which is another documentation for a train split. I just took the documentation and based it off of that. So again, I took the example and then kind of worked with this example so that I could fit my program. So X train, X test, Y train, Y test, train test split, X, Y test size 0, random state. So I think I copied and pasted this exactly just to test it out. I actually knew and understood how to use it, so it made sense. But yeah, I just set my variables as X and Y, so I didn't have to change anything else. So I trained this. Now let's take a look at this. Let's do X underscore, let's do X dot shape. We should expect this to be on the same size as the feature vector, which is like 7,000 by 4. All right. If we take a look into X train, we should expect 70% of this, which is 5,000, because we only take 70% for training and then 30% for testing. And we should expect X test to be, I don't know, like 2,000. Yeah. You do these little tests to make sure that you're doing this correctly and that your dimensions make sense. Now let's go into the random forest classifier. Again, you go into the documentation. You take a read of the parameters, and then you take a look at the example. Right. You take a look at the example, make sure what it is. I found that, oh, I don't need this. And this is important to actually understand the documentation. You don't need some of these lines, right? You don't need some of these. You can just copy and paste the rest and delete whatever you don't need. And I found that I only need these 2 lines, which include random forest classifier, max depth of 2, going 2 layers down. You can change the parameters as you want, but I took exactly what they had for the documentation. CLF, which is going to be our model, fit, X train, and Y train. So you're training your model using X train with the labels, right? You're using your data set as well as the labels to be able to train whatever model you want. Prediction now, it's common, like it's common to use these type of variables where it's X train, X test, Y train, Y test, Y underscore predict. Please be familiar with these, because this will help you. This will help you in the long term, because it's going to be consistent with everybody, right? Rather than doing like label underscore prediction or something, just do Y underscore predict. Like it'll make a lot more sense. So it'll be model.predict, which is just a function of X test. You could obviously take a look more into exactly what this is, but then again, oh, sorry, wrong documentation. Then again, it's in this documentation right here at the bottom, where you see X fit. Oh, actually, no, this one doesn't have predict. But yeah, you just search up predict, model predict on Python, and then you just find an example, and it just happens to be clf.predict. Right? And then you predict your X test. So now you have, what do you have? You have your X train, you have your Y train, which you created for your model. Right? Remember the 4 steps I mentioned earlier. You want it to be able to feature extract. You want to train your model. Now you have trained your model. Now you want to test your model, right? Which gets you Y predict. Because now you introduce your model to these new samples, and now they're creating a label for those samples. Now you try to get the accuracy. One of the functions that you introduce is Scikit-Learn. You could do this also by hand, like with your own function as well, but it's obviously easier just to call a function. Accuracy score of Y test, which is, what is Y test? Y test is your official, like your legitimate label, and then your Y predict. And then you just print out the score, which gets you a 52% accuracy, which is horrible, but makes sense. And why does it make sense? Because you're only using one axis of the entire human activity recognition to be able to try to determine an activity. We took a look at x-axis for standing, and we didn't even know what that was. It just looked like a random signal. We had x-axis for the walking upstairs, which looked like walking, but how do you differentiate between walking upstairs and walking downstairs? And you can take a look more into the different like plots to be able to see this, but this is just an introduction to exactly what I'm trying to explain, right? And it makes sense for 52%, right? Does anyone have any comments on this? Right. So now let's do a quick summary. we learned to open a file using Panda. We extracted features using Numpy. We also created a feature vector using Numpy. And then we used decision tree from Scikit-Learn. Next week, my data didn't save. What? Oh, that's so annoying. That is so annoying. I hate when this happens. Next week, what we're going to do, or next week, or the next time we have an opportunity to be able to do this, I'm going to be able to do all of this. We're going to go a lot quicker. We're going to extract the specific feed. We're going to extract another file data set. We're going to extract our feature vector as well. And then we're going to apply a more convoluted machine learning algorithm. And we're going to figure out the hyperparameters that work well with this example as well. So we're going to continue using Scikit-Learn. We're going to use LSTM, which is a really, really good machine learning model for time series, which is what we have. And it's going to get us a high accuracy. And I'm going to walk you through more steps of how to actually figure out which machine learning model you want to use, the hyperparameters that you want to figure out so that you can get the best accuracy that you can possibly get.